Here are solutions to homework set number 4 for ECE 341 random processes. This homework looks at binomial and uniform distributions. Now the first problem is if you're playing Dungeons and Dragons, when something happens like you get hit with a petrify ray, you can roll a saving throw. If you save, no damage, otherwise you're petrified. Suppose you save on a 14 or higher, meaning P is 7/20. What's the probability of making 7 saving throws and 10 rolls? So basically you don't like making saving throws because eventually you'll fail and you get petrified. So suppose you get hit with 10 of them. What's the chance you're going to save 6 times out of 10? That's a binomial distribution. The PDF for a binomial distribution is n choose m, where n is the number of coin tosses, m is the number of successes, p is the probability of success. So with 10 tosses, 6 successes, I've got a 35% chance or 7 in 20 chance of succeeding, 65% chance of failing. P is 6.8%. In problem 2, I can solve this a different way. I can use convolution. For a binomial distribution, it kind of looks like this. If this is 0 and 1 save, the probability of failure is 0.65. Probability of a success is 0.35. So I can do that as a polynomial. That would be 0 plus 1x, where x is e to the minus 1. Well, let's try this again. So in terms of z transforms, this would be 0.65 plus 0.35 over z. That's the z transform. If I do this twice, I square the z transform. 10 times, I raise it to the 10th power. So what I'm really doing is I'm trying to find out what polynomial is this to the 10th power. Multiplying polynomials is convolution. So what I can do is take a single coin toss, convolve it with itself, gives you 2 coin tosses, convolve that, you get 4 coin tosses, convolve that, I get 8 coin tosses, convolve 8 and 2, I get 10 coin tosses. Now if I check, here is the number of successes, here's the probability, and successes matches up with what I did before. So either method is valid. Convolution is actually a lot harder. Unless you have MATLAB, then it's actually easier. But gives you the same answer. Plus, convolution gives you the probability of each number of successes. So being 10 out of 10, basically it's not going to happen. Problem 2. If you go to the National Oceanic Atmospheric Administration, NOAA, they've been monitoring world weather for 142 years. 27 of the last 30 years have been in the 30 hottest years on record. What's the probability that's just chance? Well, this is a binomial distribution. I've got a coin toss. The probability of any given year being in the top 30 is 21%. If I flip the coin 30 times, I get 27 heads. What's the chance that that's just random chance? Well, if I calculate it, it's 30 choose 27, 0.21 to the 27th, 0.78 cubed. Here's the probability that if you just selected 30 years at random, 27 would be in the top 30. Which is, as Ted Cruz would say, proving that this could just be chance. There is a chance this is just random. Not real likely, but there is a chance. Problem 3. This looks at uniform distributions. With a uniform distribution, the probability of all outcomes are the same. So if I roll a 10-sided die, the probability of each number coming up is 1/10. That's for numbers between 1 and 10. Suppose I roll 4 10-sided dice. What is the PDF, the mean, the standard deviation, and the probability that I roll 30 or higher? Well, there's a couple ways to approach this. If I use z transforms, or moment generating functions, whatever your favorite name is, I actually wind up using convolution. The z transform of a 10-sided die is just 1/10 delayed by 1, 1/10 delayed by 2, 1/10 delayed by 3, and so on. I could rewrite that putting over a common denominator. That's for a single 10-sided die. If I roll 4 10-sided die, I just multiply x by itself 4 times, or raise it to the 4th power. So there's your answer. That's the z transform of y. Well, to multiply polynomials, I wind up using convolution, so I'm kind of stuck using convolution either way. So, second way to do it is just convolve. Here's the PDF for a single 10-sided die. I'm not going to roll a 0. Here's 1 through 10. 2 10-sided dice is convolve it. 4 10-sided dice convolve again. And if I draw the bar chart, here's what it looks like. So that's the PDF of 4D10. It's got a nice bell-shaped curve. That's the central limit theorem. We keep seeing that over and over again. To describe this curve, oftentimes we use the mean standard deviation. So the mean is just what's the average, the weighted average of each number. So the probability was 10d4. The value is just n. Add them all up, I get 22.0. The variance is the distance from the mean squared. So take each number, how far it is from the mean, square it, times its probability. I get a variance of 33, take the square root, 5.7. And kind of notice the variance is what adds, not the standard deviation. The probability of doing 30 or more is just add. Take all these areas, add them up, and that's the probability of doing 30 or more. Add them all up, I get 9.97%. Now a couple people did 30. That's kind of an anomaly with MATLAB. MATLAB hates the index 0. So the first guy right here, probability of getting 0 is actually index 1. 1 is index 2. 30 is index 31. So just because MATLAB hates 0, everything's offset by 1. So this is actually going from 30 to 40, or index 31 to 41. Problem 5. If I do an ice storm spell that does 4d6 plus 2d8 in damage, find the PDF, the mean standard deviation, and probability of doing 30 or more. Again, since I'm going to wind up using convolution anyway, so let's just use convolution. Here's a single 6-sided die, it's PDF. An 8-sided die, it's PDF. Convolve them, I get 2d6. Convolve, I get 4d6. Convolve the d8s, I get 2d8. Convolve those together, I get 4d6 plus 2d8. Graphing them, here's what it looks like. Again, nice bell-shaped curve. To find the parameters, this is the weighted average, the mean. This is the weighted distance from the mean squared, the variance. Take the square root, I get the standard deviation. And once again, add up all these bars between 30 and 40, offset by 1. I get 8.5%. And finally, I don't know what the spell is, but if there was a spell where you roll a 4, 6, 8, 10, and 12-sided die, what's it look like? So again, I'm going to use the PDFs, PDF of 4, 6, 8, 10, 12-sided die, convolve them all together, plot them, that's what it looks like. Again, a bell-shaped curve. That tells you that's a pretty important distribution. We keep seeing it over and over again. Mean of 22.5, variance of 29.5, take the square root, standard deviation 5.43, and the area to the right, probability of 30 to 40 is 10%. Now these last numbers we're going to compute again when we get to a normal distribution. If you note, this is a nice bell-shaped curve. That's the central limit theorem in action. If I approximate that with a normal distribution, I can calculate basically the same odds. It's the area of this tail. The advantage of a normal distribution is I don't have to go through all this convolution. There are shortcuts. But that's coming up later. That and get back to the ranch. That is homework set number 4 for 341.